Okay, so it's my pleasure to introduce Vasileios Verykios, who's a professor at Hellenic Open University in Greece. I've done a bit of work with Vasileios over the last few years. One of his main research interests is privacy-preserving record linkage. We've seen a lot of people talking about Bloom filters, but Vasileios has actually done different kind of approaches of how we do privacy-preserving record linkage. So I'm looking forward to hear about your latest work.
Thanks very much, Peter. Thanks for being here. What I'm going to present is a joint work with a team of people that we're looking into some issues related to privacy-preserving record linkage, and a large portion of the work will be included in the doctoral thesis of Dimitrios Karapiperis, who is finishing his PhD very soon. First of all, a small introduction about the title. Privacy-preserving record linkage is all about comparing records in order to find out whether they link, whether they match or not. In order to do it in a private way, in a secure way, you have to do some kind of transformation to the original records. This is what the space embedding is all about. So there is some space, like the Euclidean space, where you embed somehow these records in order to be able to compare pairs of them in order to find whether they match or not. So this is the reason why we use this title, and some of the techniques I'm going to present are related to this embedding into some spaces that allows us to make the comparison easier by using some of the properties that these spaces are offering to us. So this is an outline of the talk. The motivation, we've seen a lot of examples, a lot of scenarios. Actually, what I'm describing here is related to what Brad presented yesterday. So, there are various health facilities where people visit and they are prescribed some drugs, and then you have to follow whether their health is getting better and things of that sort. And people visit different hospitals and different pharmacies to buy drugs and so on and so forth. And all this information is sensitive, related to illnesses, related to identifying information about the patients and so on and so forth. How do we go about integrating this information if we have to deal with this kind of sensitive information? So this is a specific example of a person that visited the two different hospitals, and we can see that there is some kind of variation in her first name. There are many applications, and the list is growing larger all the time. Financial, banking applications, census correction studies, and so on and so forth. So I'm going to give you an idea of the steps, the phases that we have to go through in order to perform this privacy-preserving record linkage. We call it a pipeline because one phase feeds data to the next phase. And so actually the classic record linkage contains the last two phases, as we call it, the searching for similar records and the matching of record pairs. I'm calling, even if in the bibliography The second step is usually called the blocking. I am calling more generally as searching because our task is to search for finding tentatively matching pairs of records. And one of the techniques that we use for searching is blocking, sorting, hashing, and so on and so forth. Now, as far as the privacy preserving record linkage is concerned, we have to add one step in front of the next two, which is the anonymization of records, because we have to somehow hide some information, and so we need to anonymize them. So the idea is, the scenario is the following one. Another thing that I have to say is that PPRL, privacy preserving record linkage, is, as we all understand, is a multidisciplinary area. So there are many areas where we can get the basic components of the techniques that we apply. In this description of the scenario, we use some kind of cryptography-based presentation. That's why we use Alice and Bob, which is a usual scenario that is used in a cryptography kind of setting. So if we think Alice and Bob as the custodians, as the owners of two databases, the problem is how these two people can link their records if the records contain sensitive information. And in this case, before we can go on with linking these records, we have to anonymize them. The anonymized records, though, actually the anonymization process should entail some kind of transformation that allows us, after the anonymization, to be able to perform the linking. So we should not lose identifying information which will allow us to link the records after the anonymization is going on. So this is the idea. I hope you get it. I will explain it further later on. So our problem, the problem that we are dealing with in this scenario is the high complexity of this problem. As we all know, I guess, if we have a database with n records and we have to link this with another database of m records, the complexity, as we call it in computer science, the difficulty of performing the linking is n times n, m. Okay, so it is, as we call it, if we want to do some deduplication, for example, and the database has n records, then the complexity is n squared, is quadratic, as we call it. So if we are talking about databases with a huge number of records, then this problem is getting computationally difficult, and this is the algorithms that we are building are used for addressing this problem, the high computationally issues related to linking records. So the problem comes not only because of the number of records, but also because of the dimensionality of these records. So we may have billions of records, but also these records may have a very high dimensionality, which is a very large number of fields, a large number of properties and characteristics. So our goal is to build some algorithms that they give us some guarantees related to the time and accuracy that they give back to us. So we don't just put the data into some algorithm and we wait there for, for a day, an hour. We try to come up with techniques that they give us some guarantees related to how fast they can run and how accurate these algorithms can be. So this is a visualization of the process. In the cryptography setting that I was talking about earlier, usually there are two very common scenarios. One scenario that Dinusa talked about yesterday is the two-party scenario, where we have Alice and Bob, and these two guys are trying to link their records without having any help from anybody. And there is, which is a difficult computational scenario because it entails cryptography oriented algorithms. And there is also another scenario, the three-party scenario, where we have Alice, Bob, and another guy, Charlie, for example, as we call it, or else a trusted third party that the first two are using in order to facilitate the linking. So since they don't want to exchange their data with one another, they select a third guy to do this job for them. So the setting is that each one of these guys, Alice and Bob, anonymize their records in a proper way, so that these records are sent to a third party, which is trusty. We called in other presentations, we are assuming a scenario that we call it honest but curious. So we assume that the third party is honest, but still if he is able to find out some information from whatever Alice and Bob sends to him, he will do it. So, but we don't have any adversary who is trying to steal information. So this is the scenario. So we are talking about a mild version of a third party that is going to do the actual job of searching, for example, finding records that are most probably will be matching records, and also matching actually those records in the sense of finding what the value, the degree of matching is, which can be somehow quantified by some number in between 0 and 1. Still, the output of this third trusted party is a set of matching anonymized record pairs. Let's see some of the techniques which have been used for these three phases: the anonymization, the searching, and the matching. So this is what I'm going to present. As far as the anonymization of records is concerned, there are various techniques. We've heard about these techniques more or less before. A work by Skanapcheko is embedding, as we call it, records to a space. A space, as the title says, is a metric space, is a space that allows us to make arithmetic numerical comparisons. But the strings are not numerical, I mean, can be any kind of data, numerical or textual data, and so on and so forth. In order to embed this kind of records into a metric space where you need to do some numerical computations, you have to transform them. By transforming and embedding these records, you gain also that you anonymize these records. So this comes for free, I guess. So what is the process of embedding that Skanapcheko is following for embedding these records into a metric space? Is that she uses let's say, a number of random strings, 4 such strings. Actually, Brad gave a nice visual representation of this process. And she actually compares, she computes the eddy distance of each of the, let's say, the first name or the last name of each record, and she finds the eddy distance between each one of the strings from the random strings. So she comes up with a number. So, and then there is a vector of numbers, and this vector of numbers is a representation of the original record, and this numerical vector is what we call as an embedding into some Euclidean space, where you can use some numerical computation afterwards. Because the approach that Skanapcheko proposed wasn't very much accurate and precise, Bonomi and some colleagues of his presented a more accurate and precise way of embedding records into a space by somehow tuning the selection of the reference, as we call it, strings. Instead of being random strings, Bonomi used some frequent Q-grams from the data sets at hand. Still another approach for anonymizing records is using some phonetic encodings. We all, maybe some of you know about the soundtext code. We've heard this technique before. So for a name like Vasilis, it produces some code like V300, for example. There are not too many such soundtext codes which entail some privacy issues. And so this is one way of anonymizing records, but it's not enough. So that's why in this work, apart from transforming the strings into the soundtext equivalent or NICEs or whatever, we also put some fake records into them to somehow augment the privacy guarantees of the proposal. Another thing for anonymizing records in our scenario is what Rainer was talking the first day of this workshop, where you extract Q-grams and insert them into a Bloom filter. This is still considered as an embedding, a space embedding technique. So the Bloom filter is an important component in our methodologies. 10 minutes. So it deserves some, further somehow description. You may remember what Rainer presented. So if we have a string like this, we break the string into these things that we call it bigrams, because they consist of 2 consecutive characters. Generally they are called n-grams or q-grams because of a paper by Gravano, and this is where the q-grams are coming from NYU. And this is a field level Bloom filter. This is the Bloom filter. This is a 0-1 representation of a string, John. And this is a concatenation of these 2 representations is a record-based Bloom filter, while in the second one we have a record level Bloom filter representation, because we are using only one Bloom filter where we put all the information about the first name, the last name, and so on and so forth. So this is a kind of transformation where an anonymization is happening in the way. With respect to searching, so I presented some basic techniques about anonymizing data. Then we move on to the next phase, which is the searching phase. There are a lot of techniques which have been presenting, mostly from data management community and data structures like tree-based techniques, hierarchy-based techniques, where you use some hierarchies. Let's say you shop things from a supermarket and you somehow generalize things. If you use such hierarchies, you can find some efficient algorithms for performing searching for tentatively matching pairs of records. Still, another methodology for searching about matching pairs is what we call it as a reference-based clustering, which is similar to the approach that Scanapieco proposed, where there are reference strings, and you take the distance of each string in your data from those reference strings. Instead of having random or some specially selected strings, you take a reference data set like from a telephone directory, let's say, or you build such a data set from your data. Anyhow, other techniques include multi-sapling techniques, neighbor-based techniques, etc. Now, I just want to concentrate on the most important technique that this work somehow is all about, which is actually the Hamming locality sensitive hashing approach. This technique guarantees that each similar record pair will be identified with high probability. This is a probabilistic technique. Actually, the embedding, the anonymization is happening with Bloom filters, and Bloom filters are considered as an embedding in a Hamming space. A Hamming space, in the Hamming space you can use a distance for comparing your transformation of represented records, which is called the Hamming distance. The Hamming distance, it counts the number of positions where both have ones instead of having 0, 1 or 0, 0. In this scenario, the similarity between a pair of records is defined by a distance threshold, which can be computed. Okay, this is the distance. This threshold is theta. So if you find a distance d which is less than theta, then this is considered as that your pair of records match. Anyhow, the technique. Yes. I'm running very late, and Dimitris will be angry, but hashing of embedding records implies that there is the key component of the technique is to use some kind of redundancy. So this redundancy comes into a number of hash tables. What is a hash table? Is a table with two columns. One column stores the keys, and the other one stores the records that have the corresponding key as a representation. So the hash table, we have a lot of such tables, and we hash the records multiple times and to multiple hash tables. And by doing this, we somehow create some redundancy in order not to lose by accident any possible matching record for another record. There are some probabilistic guarantees that this approach comes with, so this locality sensitive approach of the space, of the Hamming space, and so on and so forth. This replication of hash tables comes with a price in performance. In order to minimize this price and to be as efficient as we can, we can find out what is the optimal number of hash tables that can give us some specific guarantees related to the accuracy of matching the records. I'm very fast now, but so yeah. So this is somehow the thing that I'm describing to you. This is a hash table. This is a second hash table. This is these are two records and the keys and how they hash to these hash tables. And this is where the buckets are. And so eventually we have to compare these two records since they have been hashed to the same bucket in order to find whether they match or not. The matching process is more accurate, so we have to spend more time in doing this. These are some results with respect to how good this approach that we have proposed, the Hamming LSH, is with respect to the completeness of pairs and the reduction ratio, which are two of the metrics used heavily in this setting. So more or less this is the kind of techniques that we are using for speeding up, as we call it, the computational issues that come up in these scenarios. And I wish I had more time, but I thought that it would be better to put some more effort on introducing the subject other than going into the... So, thank you very much.
I think given the time, I want to make sure that Andy has enough time as well. Let's postpone questions to the tea break, right? Tomorrow and then Friday, so you can...
Sure.
Otherwise, we're going to run out of Andy and us. So, thanks, Vasileios.
Thank you very much.
Good going.